Hey guys, so welcome back. So I just got my hands on the 2022 VCE physics exam paper. So I'll try to blitz through these questions as fast as possible, try to go through the solutions, but also try to give a little bit of explanation as well, just for the current year 11 physics students so they can actually follow through a bit better and actually learn the content as well. All right, so let's get started. All right, let's go with question 1 here. By the way, guys, for any MCQ questions where the options are a bit vague and it's not 100% clear which one's right, which one's wrong, just know that VCAR examiners do sometimes give marks for two answers, for two options, so you actually can get a mark if you pick either one. So for that question, I'm assuming that VCAR can take both of those options, right? At least because it's a bit vague as well with the options and with the wording of the question. So I'm assuming that it's something along those lines. And even if not, it's just a 1 mark question, so it's not that big of a deal. All right, so we have a DC motor question here. Right, so we have 4 positions of the DC motor as shown, submerged in a uniform magnetic field. Right, so our coil is turning in the uniform magnetic field that is parallel to the plane of the coil when the coil is at position 1, of course, and then it rotates in a clockwise direction to the middle of the sides L, M, and NK in the direction indicated. Force that is acting on side KL. Right, so since our coil is moving in a clockwise direction, right, our magnetic force will be going upwards. Right. So if we use our right-hand palm rule, we can then find the direction of the current. Right. So with the magnetic force being upwards, our fingers pointing to the right, our palm happens to sorry, my bad, I completely messed that up. With our fingers pointing to the right and our palm pointing upwards, we can see that current has to flow from K to L. All right. All right. Moving on. When the coil is in position 3, in which direction the current is flowing in the side KL? So we are asked to state that. So in position 3, so let's have a look at this. In this case, our magnetic force has to be pointing downwards. So our palm has to be pointing downwards. Our fingers are still to the right. Right. So if you just quickly twist your hand, you'll realize that the current is indeed flowing from L to K. Right. Not gonna be a bit awkward twisting and molding your hands, but to get used to it. So the current flows from side L to K. So the current swaps direction, and that's the whole point of the DC commutator in the first place. Swaps the direction of the current every half turn. So the side KL of the coil has a length 0.1 meters and experiences a magnetic force of 0.5 newtons due to the magnetic field, which is a magnitude of 0.5 Tesla. We asked to find the current in the coil. Right. So we can sub all of these values into this formula, assuming that our coil is only made up of a single turn, and there's nothing in this question that indicates there's more than one turn, so we can make that assumption. All right. subbing all of these values in, we get 3 amps as our answer. So hopefully you guys got that right. Alright, so here's the first real worded question in this paper. So we're looking at a diagram of a geostationary orbit above the Earth in circular orbit. The orbit has a period of 1 day. That's the definition of geostationary. The geostationary satellites remain stationary in relation to a fixed point on the equator. Figure 2 shows an example of a geostationary satellite that is in orbit relative to a fixed point x on the equator. Part A, explain why the geostationary orbits must be vertically above the equator in order to remain stationary relative to the Earth's surface. So a geostationary orbit can't be generated from any point in any axis along the surface of the Earth. For example, if you have a satellite up over here, right, and it has a velocity, let's say, going in this direction, the gravitational force is always going to point towards the center of the Earth, right? And that is going to cause this satellite to orbit in almost like a diagonal along the surface of the Earth. I'm not sure if you guys can sort of see that. Maybe a better diagram might be something like this. So a satellite can actually move diagonally, right, with relation to the surface of the Earth, because the Earth is always moving along the equator, right? The Earth is always moving along its vertical axis, or almost a vertical axis. So it's moving horizontally, right? The Earth is orbiting horizontally. So our satellite must orbit horizontally as well. And for that, we need the satellite to be above the equator. It can't be above any point on the Earth for a geostationary orbit, right? For its motion to match up with the motion of the Earth. So the Earth orbits around its axis in horizontal motion, which this satellite must match. So the satellite must always match that motion. So this is a sample response for you guys. So the satellite must be above the equator such that the center seeking or the centripetal gravitational force, you guys should write gravitational force in full words, not FG, but I'm just running it here just to showcase it to you guys, which causes it to move in motion with the Earth along the same plane. So those are like the key terms that you guys can use. There's different ways of wording this. It's not a set in stone response, but you guys should write something along these lines. You can also draw a diagram like I've done over here to illustrate what will happen if the satellite isn't above the equator, right? Even if the period matches up with the period of rotation of the Earth, it will still not be in geostationary orbit. All right, so here is a 4-mark calculation question. Using these above values, you have to show that the altitude, so that's a really important word, of the geostationary satellites must be equal to this value. So let's just combine everything we know about this scenario. Right, so we know about the period of orbit of this satellite. The satellite's orbit must match exactly with the orbit of the Earth, right? So the satellite must take 1 day to rotate because the Earth takes 1 day to revolve around, right? So that is our period. We also know the mass of the Earth, of course we do, and we also know for a fact that the gravitational force is acting as the centripetal force. So those are like the 2 key ideas that form the pillar of this question. All right, so let's combine everything together. Right, we asked to find the value of the altitude, so that relates to the radial distance. Right, so subbing all of these values in, we get that R is equal to 4.2 0.23 times 10 to the power of 7 meters. If you subtract the value of the radius of the Earth from this, right, you will get your answer to be 3.59 approximately times 10 to the power 7 meters. All right, moving on, let's calculate the speed of an orbiting geostationary satellite, which is pretty interesting because I actually use the speed formula in my calculations, but there are different ways of doing part B, right? There are a lot of people who would have just memorized this formula down, right? Or you can write this down in a cheat sheet, but I always like to derive these formulas just so I have less to memorize. Okay, we know the radius, right? The radial distance, and we also know the period. So we can use the definition of the speed. So this is actually not that hard of a question, right? At least if you remember your basics. Alright, so making the substitution for our period, we get that the speed is equal to 3.1 times 10 to the power of 3. Alright, so let's move on. Alright, so question 3. We've shown a schematic diagram of a mass spectrometer that is used to deflect charged particles in order to determine the mass as shown in figure 3. Positive singly charged ions with charge of this value are produced at the ion source. These are accelerated between the anode and the cathode. So the cathode, I'm assuming, is negative. The potential difference between the anode and cathode is 1,500. Alright, so let's just jump on to question A. We know the value of the voltage already. So I'm assuming we can do the kinetic energy of each ion as it passes between the anode and the cathode. Alright. So we have to use this formula. Work done is equal to the change in energy, which is equal to QV. In this case, the change in energy is just going to be the change in the kinetic energy, right? And we're assuming that the initial kinetic energy is 0. Right. So the final kinetic energy, are we assuming, oh no, sorry, we cannot assume that the initial kinetic energy is 0 because we only asked to find the increase in the kinetic energy. So we can just write out delta E, which is equal to QV, making these substitutions. Right, so we will get 2.4 times 10 to the power minus 16 joules as our answer. Moving on, part B. Each ion has this mass, and to show that the speed of the ion is this much as it exits the cathode. Alright. Assume that the ion leaves the ion source. Alright, so we actually do make the assumption that I was talking about. The initial kinetic energy is 0. Right, we already know the work done value. So that means we already know the final kinetic energy just from this. Now the final kinetic energy is given by half mv squared, right? So of course, if we extract the value for the work done, right, making the substitution. Remember guys, you'll always get 1 mark for subbing in the values into the formula, or as long as you, at least if you write down the formula. Alright, and we do indeed get 3.16 times 10 to the power of 5 meters per second. Alright, now we have to look at the magnetic field part of the question, which is given by this magnitude. We have to calculate the diameter, which is double the radius, of the semicircular path followed by the ions within the magnetic field. Alright, so we have to use the relationship between the magnetic force and the centripetal force. Now, if we isolate R, which again is related to the diameter, we will get that R is equal to mv over qb, since one of the v's cancel out. Right. Now the diameter is just equal to twice the radius. Right. And this value of the speed is what you would get from the previous part of the question. Alright, so our answer would be 0.19 meters. Alright, always good to double check, so substituting the mass, substituting the charge, and magnetic field strength, make sure everything is in the standard units, no kilonewtons or grams in here. Yep, so that looks about right. Right, now let's move on to question 4. This looks to be an EMF question, but not 100% sure. So we have a square loop of wire connected to a resistor placed close to a long wire carrying current I in the direction shown in figure 4. The square loop is moved 3 times in the following order. It starts at position 1 and it rotates 1 full rotation at a steady speed. Right, so that's constant about the x-axis. The rotation causes resistor R to move first out of the page. Okay, so it's sort of moved in a clockwise direction as viewed from this perspective. It is then moved downwards parallel to the current carrying wire, position 1 to position 2, and then position 3. It is taken to move at a constant speed perpendicular to the current carrying wire. Okay, so we have to sketch 3 EMF time graphs, sketching any EMF generated in the square loop during the motion of the axis provided. So this is really, really good. So this is actually a really good question because it sort of highlights how the different motions of a coil with respect to a magnetic field affect the EMF graph, or the shape of the EMF graph. Okay, so we know here for a fact that we're going to have our magnetic field. All right. Now we're going to have a magnetic field pointing into the page in this case. Now, when our coil is rotated in movement 1, we're going to have a change in magnetic flux, and it's going to be a sinusoidal. Now you may notice that the induced current in movement C and movement A is exactly the same, so that might raise some eyebrows. So let's look at the difference between the two movements. For movement A, we are rotating, and we rotate for one full rotation about the x-axis. So that means that our magnetic flux decreases into the page first, and then it also starts to increase into the page as well later on. Right, so there's a bit of there's an AC generation going on over here. Right, so we're decreasing into the page first of all, right? But then after the coil reaches a horizontal position, it starts to move back up again, and then we're going to start increasing into the page. Right, so that is the whole idea. So we're going from we're alternating between our magnetic flux changes are first decreasing into the page, and then they're going to start increasing into the page as well. So our current actually swaps direction as well, believe it or not. So we are going from clockwise to anti-clockwise, right, to clockwise and back to anti-clockwise. So in this case, on second thought, our answer is actually alternating, so we produce an alternating current. You can also just directly get the answer just looking at the diagram where it looks like an AC generator. So that is the answer. Right, so moving on, we're working towards our transformers here by the looks of it. So we have a wind generator providing power to a factory 2 kilometers away. When there is a moderate wind blowing steadily, the generator produces an RMS voltage of 415 volts and an RMS current of 100 amps. So RMS is important, so we use this averaged out values. The total resistance of the transmission wires between the wind generator and the factory is 2 ohms, and this is the total resistance as well. So we don't need to double up on anything. We have to calculate the power in kilowatts produced by the wind generator when there is a moderate wind blowing steadily. Alright, so power is given by current times voltage. And so that will get us an answer of 41.5 kilovolts. Alright, so moving on, to operate correctly, the factory machine requires a power supply of 40 kilowatts. Determine whether the energy supply system, as shown here, will be able to supply power to the factory. Okay. Alright, so we have to use the energy conservation principle in order to determine this. What is the power that reaches the factory? Okay. So the power that is outputted must equal the power that is lost due to heat and sound and whatnot in the transmission lines, plus the power that is supplied to the factory. So we have two means of power loss. So therefore, the power that the factory receives must be the difference between the output power and the power that's lost. All right. Now, the challenge here is to determine the power loss. In this case, we know the resistance, right? We know the total resistance. So this distance value actually doesn't mean anything here because we know the total resistance in the transmission wires and the wind generator. If we were given like a density of the resistance or something like that, then that 2 kilometers would actually matter. So in this case, we just need to take the power loss, which is I squared R. If you guys did V squared over R for this question, unfortunately, that would have given you a wrong answer, right? Because you don't know anything about the potential difference. We only know the voltage value, but only one voltage value, 415 volts. That's only one value. So in this case, if we make these substitutions, we will get 20 kilowatts as our value for the power. So this value is in watts, by the way, but I just convert it into kilowatts. Right, so therefore the power that the factory receives is actually much less than what is required. Right, it's only 21.5, which is less than the required 40. Right, therefore enough power unfortunately will not be able to be supplied. Right, now of course we have a transformer, because that's the whole point of a transformer, to reduce the energy loss in our wires. So to limit the transmission energy loss, we install two transformers: a step-up transformer, which steps up the voltage, steps down the current, and a step-down transformer, which steps up the current and down the voltage. Right, they have the same ratio of turns. With the installation of the transformers, determine the power now supplied to the factory. Alright, so the key idea here is we need to first of all find what the power loss is. Okay. Alright, so look in this diagram. We have a step-up transformer that connects the transmission lines with our power generation system. Right. Now, in order to find the power loss, we know we needed to first of all find the current, the new value of the current in the transmission lines. Alright. So if we make these substitutions, we will get that our final current is actually reduced from 100 amps, right, over here, to now only 10 amps. So our power loss, which is given by, again, I squared over R, that will now be reduced by a factor of 100, right, believe it or not. Right, so that is a pretty big reduction in the value of the power loss. Right. So therefore we can say that the power received by the factory will be equal to the initial power that's supplied and the power that is lost. So I think I made the wrong substitutions here. It should be 41.5. Yeah, so that's the power that's required. 0.3. Yeah, sorry to give you guys a heart attack there, but yeah, it is 41.3 kilowatts. All right, so this factory will actually work this time, but we don't need to write that because that's not what the question really cares about. We don't need to do anything to the step-down transformer here, in case you guys are wondering, because we only deal with that power loss, and the power loss only depends on the current, according to this equation. And so we only care about how the current is changed. All right, so let's move on. So here we're looking at, again, an alternator, right? So a lot of alternators here. Simple alternator with this much area and 200 turns rotating in a uniform magnetic field. The magnetic flux through the coil in the vertical position is shown in figure 6 and is this value. So we have to use the value of the magnetic flux as we can see here. So 1.2 times 10 to the power minus 3 Webers is our magnetic flux. We also know the area, right? So if we rearrange this, we can get our value for the magnetic field strength, which is 0.02 Tesla. Part B. The rectangular coil rotates at a frequency of 2.5 Hertz. We have to calculate the average induced EMF produced in the first quarter of a turn. So we're going from maximum flux to zero flux, right? Maximum to zero flux. So that is our change in flux. We have to begin the quarter with the coil in the vertical position. All right, so that's cool. First of all, we need to find our delta T value. So we can do that by taking the reciprocal of the frequency, right? So 1 quarter turn takes a quarter of the period time, right? It only takes 0.1 seconds to occur. That's another key mistake that a lot of people make. So to bear that in mind. All right, so you can either write your expression in this format, or if you guys are a bit smart, you can also write this in a bit more of a concise way. We know for a fact that the magnetic field strength is the same, but the area is changing, so you can also write it in this format. So you can change the flux in this way, where you change the area without actually changing the magnetic field strength. All right, the magnetic field strength is 0.02, and the first initial value of the area is 0.06. So this is not the area of the coil as a whole. This is the area that's exposed to the magnetic field. So don't think that the coil is shrinking. It's just the area that's exposed to the magnetic field is changing. That's the only difference. All right. So here I get a value of 2.4 volts. So that seems about right. Correct me if I'm wrong in the comments, but that seems right to me. All right, so finally we passed area of study 1 and 2. So Kim and Kelly are experimenting with trolleys on a ramp inclined at 25 degrees. They release a trolley So a Formula One racing car is traveling at a constant speed of 144 kilometers per hour around a horizontal corner of radius 80 meters. The combined mass of the driver and the car is 800 kilograms. We have to calculate the magnitude of the net force acting on the racing car as the driver goes back. All right. So here we have circular motion, and of course we know circular motion, we look at the centripetal force formula. Right. Have no clue why they gave the speed in kilometers per hour. They already gave us the value in meters per second anyway, so no clue why that's there. Alright, so let's move on. On figure 8b, draw the direction of the net force acting on the racing car. Right, so that it will just be the centripetal force. Explain why the racing car exerts a net horizontal force to travel around the corner and state what exerts this force. Alright. Bit of a controversial question. I never knew this stuff was actually in the study design, but it is the friction force of the tires and the track. Which is what it is state. Alright, so these are the 2 points that will give you your 2 marks. Due to the track being rough, a frictional force exists, and the wheels of the track are orientated sideways, so they have to tilt sideways, right? You have to turn your wheel around. You can't have your wheels straight, right, forwards for you to make a turn. So you need to tilt your wheels around to make a turn, so such that the friction between the wheels and the track acts as this horizontal force, right, as we can see here. Now, moving on, question 9. We have a star that's transforming energy at a rate of 2.9 times 10 to the power 25 watts. Explain the type of transformation. Alright, so this is a pretty general question, and what effect, if any, the transformation would have on the mass of the star. So we can completely ignore that value because that's pretty useless. It's a word question. 2 marks, so 2 dot points are needed. Don't need to write in dot points, but I feel like it's the best way to structure your answer. Any worded question of energy should involve the principle of energy conservation, right? So you guys can just write this down. Always makes a good impression on the examiners. Don't know if there's meant to be an apostrophe there, but this is your response. So we will use the conservation of mass energy from special relativity. If we are outputting energy, it can either come from other forms of energy or it can come from mass. Right, so moving on, we actually have an experimental question. Wow, halfway in the paper. Okay, that's a change. So physics students use a tennis ball launcher on a level outdoor oval on a wilderness day to investigate projectile motion. The tennis ball launcher can be set to project tennis balls at speeds u between 8 meters per second and 30 meters per second, and at angles theta between 10 degrees and 80 degrees. Standard tennis balls of mass 56 grams are used. Students in this experiment can be classified as controlled. The variables, not the students, can be classified as controlled, dependent, or independent. Okay, so in this case, we are going to be we can change either the speeds of our ball or we can change the angles, and that's going to affect something about the range, I'm assuming. So we are measuring the range, right? Of course, our speed is fixed, and the independent variable in this case seems to be the angle. Yeah, we are changing the angle. The students set the tennis ball launcher to project tennis balls at 25 meters per second. We are trying to vary the angles and see the effect on the average range. The students repeat each experiment at each angle 3 times to reduce the effect of random errors. And we have the data in the table. So quickly sketch this graph out for you guys and we'll meet up. 41 meters for around 43 degrees. Alright, now let's analyze this a bit further. So students think that air resistance on the tennis ball may affect maximum. Yeah, like no duh. They decide to compare their data to the theoretical range achieved when air resistance is ignored. Alright, so we can calculate the theoretical range for a projectile launched at an initial speed of 25 meters per second with an angle of 30 degrees. And this is the value that we get, just plugging and chugging into our calculator. Alright, evaluate whether the effect of air resistance can be ignored by the students when analyzing their data. Okay, so the range that we calculated that was theoretical, right, turned out to be 55.323 meters at 30 degrees. Right. Now let's compare this to our actual raw data point at 30 degrees, right, before we make our conclusion. So at 30 degrees, we got 37 as our average range. All right. And so from this, it is clear that air resistance is a significant variable. So the band at point C is a bright band. Explain why the band at C is bright and why there is a dark band on the left and right of this, of the center. You guys can also explain this in terms of phase differences and how for destructive interference your light has to be out of phase by half a wavelength, but you don't need to necessarily include this because this is just a 2-mark question for this case. But it would be great if you guys do include that, right? The experiment performed by the students is often described as Young's double slit experiment. Explain how this experiment gave support to those who argue that light has a wave-like phenomenon. All right, so let's jump onto it. So I've described both diffraction and the interference of light, which I'm assuming is required to get those 2 marks. We need to provide 2 distinct pieces of evidence. You can still get the 2 marks if you describe just interference, but it still a little bit talk about diffraction as well, at least hint at the idea of diffraction. Interference does somewhat relate to diffraction. All right, so the frequency of laser light is this much. Now we have to calculate the spacing of the dark bands on the screen. Right. we have to of course use this formula. Alright, so the students decide to safely immerse the entire apparatus in a liquid. The refractive index of the liquid is unknown and it is greater than the refractive index of the air. Using the same laser light, they notice the spacing of the bands changes. Alright, so let's have a look at this. What will happen to our wavelength first of all? Alright, so when submerged in a different solution, our speed of light actually decreases, right? Because our refractive index will increase. All right, so we already know the fringe spacing formula. So let's see how the wavelength of light is affected. All right, so that's the important detail here. The refractive index of the liquid is unknown, but it is greater than the refractive index of air. All right. Now, when speed of light changes in a different medium, it's not its frequency that changes, and it's not both frequency and wavelength that changes, it's only the wavelength that changes. So the wavelength of light in the liquid, right? Not the wavelength of the liquid, but the wavelength of light in the liquid is less than the wavelength of light in the air. So that means the fringe spacing in the liquid is less than the fringe spacing in the air. You guys can write this in words or in this inequalities, whatever helps you. So centimeters. So now the green LED light is replaced by a narrow beam of white light, right, which is a collection of different colors. Describe the color of light that arrives to the left of point X, at point X, and to the right of point X. So at point X, it will just be green light. So each unique color of light refracts by a unique amount because they have different refractive indexes in a different medium. Alright, so this will be the beam of green light, right? Now let's look at blue light, for example. So you have to remember our color spectrum here. So blue light is cooler than green. Right? You can just write this. You can write cooler light as your response in that table. So blue is a cooler light, and so it will have a larger refractive index, right? Hence a smaller angle. So this will be blue light over here on the left of point X. And red light, well, that will be somewhere like this, right, to the right. Now these aren't necessarily colors that are to the left to the right of point X, like exactly to the left or the right, but this is where green light is enclosed, right, between blue and red. All right. So moving on, looking at this photoelectric effect diagram, we are shown a photocurrent voltage graph, knowing that the current is given in milliamps. We have to identify what point P represents. Just identify, so no need for any explanations. That is, of course, our stopping voltage. Sam then significantly increases the intensity of light. Sketch the graph in figure 14. Let me just see if there's no caveats in the question. No. Okay, so it chooses a green filter. That's about it. Right. Sam replaces the green filter with a violet filter, so higher frequency. We have a higher frequency of light, keeping the light source at the increased intensity. Sketch the resulting graph, and the dashed line represents the original data. Right, so we're going to have a new stopping voltage. Right. And this seems about it. Right, so now we have a kinetic energy frequency graph. I'm not sure why this inner graph isn't given by a dashed line. That's not a problem. Alright, so we have to analyze the work function in electron volts of the metal surface in the experiment that produced the data. Alright. The work function, so that's not the work function, that's the flux. Work function is going to be equal to the negative of the y-intercept. So that is just equal to 3.4 electron volts. So from the graph in figure 16, calculate in joules seconds the value of Planck's constant. Alright, so Planck's constant is given by the gradient of of our kinetic energy frequency graph. So we have to use rise over run, right? It doesn't matter whichever points you choose, as long as you are consistent. Pick the points on the line. In this case, pretty straightforward. You pick those 2 points, nice and easy. So we're given 2.38 times 10 to the power minus 14 electron volts. If you want to convert this into joule seconds, you can just divide this by, also multiply this by the charge. So we get 3.8 times 10 to the power of minus 33 joules seconds. State one limitation of the wave model in explaining the results of the Fibonacci effect. Surprised there's only one question on this for 1 mark. I suppose there was a question for the double slit experiment like that, but no problem. So one limitation. While we can pick any, there's so many to choose from. We can say how the frequency of light actually affects the stopping voltage, right? We can say how the intensity of light affects the amount of current. And it's not the frequency of light that affects the current. Or we can also talk about the time delay between firing a light beam and emitting electrons, right? So now we have a energy level diagram. So here we have the energy levels of excited neon atoms, and to show that the energy transition required for an emitted photon of wavelength 640 nanometers is 1.94 electron volts. Of course, you guys should be subbing in your values into this expression. So moving on to part B, we have to draw an arrow to show the transition that would emit the photon described. So let's try to find 2 lines that have a difference of 1.94 electron volts. Right, so just skimming through this, this seems promising. So going from 19.8 electron volts to 21.74, well, that will result in this energy difference. In this case, we're emitting a photon, so we have to go from a higher energy level to a lower energy level. Right? If we were absorbing a photon, it would be the other way around. All right. No, that's it. Right, so moving on, we're here comparing the diffraction patterns of electrons, right? And oh no, we're not comparing the diffraction pattern between anything really. All right. So electrons are passed through thin metal foil, and we see this diffraction pattern. The electrons contain 10 kilo electron volts of energy. Using this, calculate the de Broglie wavelength of the electrons. All right, so let's try to see what we need to find and what we need to know before we get there. So de Broglie wavelength is given by Planck's constant over the momentum. So we're missing this value of v. We need the speed, and speed is related to energy, as you guys would hopefully intuitively understand. So if we assume that the electrons start from a zero speed and they're supplied at the 10 kilo electron volts of energy, right, by whatever device we're using, then we can calculate the speed. All right, so we can work backwards using that idea. All right, so first converted the values into joules, then found the momentum, and then found the de Broglie wavelength in nanometers. All right, so let's move on.